Shapes of atomic orbitals. Before discussing the shapes, let us discuss about some graphs related to the radial wave function and radial probability density of electrons present in different orbitals. Okay, these two graphs represents the radial wave function psi r against r. Okay, r is the distance of electron from the nucleus, and we can see the graphs are different in the case of two different orbitals. In the case of 1s orbital, one graph is obtained, and 2s orbital we will get another graph. Okay, so the plots obtained are different. If we notice, we can see that as r increases, psi r decreases slowly and reaches a minimum value 0 in the case of 1s orbital. Now, in the case of 2s orbital, the plot is different. It first decreases to 0, then it again decreases and reaches to a minus value, then increases and reaches 0 again. Okay, this is the plot. These are the two different plots for two different atomic orbitals. Now, let us discuss in the case of radial probability density curves. Radial probability density is psi r square against r. We will get the same graph and as in the case of radial wave function for 1s orbital. So, here also same graph for 1s orbital. Okay, but in the case of 2s orbital, we can see that first it decreases and reaches a minimum of 0, reaches a value 0. So, here the probability density is 0, then it increases and it again decreases to 0. And the point at which the psi r square reaches 0 is called as node. So, what is mean by node? Node means the region where the probability function, okay, that is psi r square, probability function reduces to 0 is called as node. Okay, reduces to 0. Okay, so 1s orbital there is no node, but in the case of 2s orbital, one node. So, depending upon the atomic orbitals, the node is changing. Okay, so we can write like this. For ns orbital, n minus 1 nodes are present. So, how can we calculate the number of nodes? We can calculate by n minus 1. Okay, in the case of first 1s orbital, n is equal to 1, so no node. But in the case of 2s orbital, 2 minus 1, so 1 node. So, depending upon n, number of nodes changes. It can be calculated as n minus 1. Okay. Shape of S orbital. S orbitals are non-directional and they are spherically symmetrical in shape. Non-directional and spherically symmetrical. Okay. Next, as n increases, the size of S orbital also increases. As n increases, size of S orbital increases. Okay, so these are the two graphs representing the spherical symmetry of 1s orbital and 2s orbital. Okay, here in this case, this dots represents the probability of finding the electron along x, y and z axis, and here this is in the case of 2s orbital. Okay, and here these dots are full. There is no space in between. There is no node in the case of 1s orbital. So, there is no gap in between. Okay. So, but in the case of 2s orbital, we can see there is a region where the probability of finding the electron is 0. This represents a nodal surface. Okay. And this dot represents the probability of finding the electrons. Okay. So, here we can see that as n increases, the probability of finding the electron or the size of the orbital increases. Okay. So, 4s is having more size than 3s, then 2s, 1s, etc. Okay. Shapes of p orbitals. P orbitals have three possible orientations of electron cloud. Okay. And they are designated as px, then py, pz. Okay. In the case of 2p orbitals, the three orientations are given. Okay. Depending upon the axis along which they orient, the p orbitals are having the shape is dumbbell shaped. Okay. So having dumbbell shaped. It's the shape of p orbitals. So in the case of 2px, the dumbbell shape is oriented along the x-axis, and in the case of y along y-axis, and in the case of z along z-axis. These are the three orientations of 2px, 2py and 2pz orbitals. Okay. Similar type of graphs or shapes will be obtained for higher atomic orbitals also. That is in the case of 3px, then 4px, etc. Okay. The shapes are similar, but and these are in the three possible oriented. The clouds are oriented in three possible ways, that is along each axis. Okay. Shape of d orbitals. D orbitals have 5 possible orientations of electron cloud. And they are designated as dxy, then dxz, dyz, dx square minus y square and dz square. Okay, these are the 5 possible orientations. Okay, these are given here. In the case of dxy, the lob is between dumbbell shape. Okay, the lob is in between x and y axis. In the case of dxz, lob is in between x and z axis. Dyz means lob is in between y and z axis. And in the case of dx square minus y square, the lob is along x axis and along y axis. And the last orientation is dz square. Here one lob, the dumbbell shape, this lob is along z axis and there is a spherical shape along x axis. Okay, along this direction. This shows, this will be the shape of dz square. Okay, so in the case of all other d orbitals, as n increases, the shape is similar. Okay, similar to this, but they have different in their energy and size. Okay, their sizes will change and their energy also increases. Okay, as the n increases, but the shape of those orbitals are similar to this. These are the different shapes of d orbitals. Okay. Next we are discussing about angular nodes and radial nodes. So what is a node? We already discussed. Node means the region where the probability of finding the electron is 0. Okay, region where probability of finding electron is 0. Okay. There are two types of nodes. First one, angular node, and second one is radial node. Okay. What is mean by angular node and radial node? So, angular node is a nodal plane. It is the nodal plane, or it is the plane passing through nucleus. Okay, it's the plane or the nodal plane passing through nucleus. Okay, and number of angular nodes equal n, L. Okay, number of angular knots will be equal to L. L is the azimuthal quantum number. Okay, so number of angular knots is equal to L. And now what is radial knot? It's the spherical surface where probability is 0. The spherical surface where probability is 0. Probability of finding the electrons. Okay, probability is 0. Okay, number of radial knots increases as n value increases. Okay, so total number of radial knots equal n minus L minus 1. Okay, that is, it depends upon both n and L. As n value or n value increases, number of radial knots also increases. Okay, now let us take one example. So number of angular knots is L and number of radial knots is n minus L minus 1. Total number of knots equal, we already discussed, that is n minus 1 values. Okay, let us take one example. In the case of 4 P orbital, okay, where L is equal to 1. Okay, L is equal to 1. So angular knots, number of angular knots equal 1. Now what about number of radial knots? Number of radial knots equal n minus L minus 1. N is 4. So 4 minus 1, that is 3. 3 minus 1, 2. So number of radial knots is 2. So total number of knots will be 1 plus 2. Therefore n minus 1. Total knots will be equal to 3. Okay, like this we can calculate the number of angular knots and radial knots. Okay.